who will talk about profiling actor utilization and communication.
Good afternoon, thank you for the introduction. I am Andrea Rosa, I am a PhD candidate at Università della Svizzera Italiana in Lugano, Switzerland. And this is a joint work done with Lydia Chen from IBM Research and Walter Binder from USE. In this talk, I will present a new profiler for Akka actors. And in particular, our profiler is based on bytecode instrumentation, and it is centered on two main metrics related to Akka actors, which are their utilization and the communication occurring between actors. So I would like, first of all, to clarify what we mean with those two metrics and why we decided to focus on them in particular. Our profiler targets two kinds of Akka applications, mainly. Applications where actors are used as computing workers, and applications where actors are used as communication endpoints. And for each of such kind of application, we try to devise a set of metrics that could be particularly useful for a user willing to analyze the performance of actors. In the first kind of application, actors are essentially employed to execute some computations on the behalf of the application. So in this case, some knowledge and information about the amount of computations executed by actors in response to messages that they receive is important. And moreover, when actors are used as computing workers, they are typically spawned in large quantities. For example, very often there are thousands of actors. And creating actors doesn't come for free. So our profiler also tracks the amount, the cost of initializing and creating actors. When we refer to utilization, we essentially refer to such metrics. And in particular, for us, utilization is also a concise metric that can compare those two quantities. So in particular, our profiler tracks the utilization in terms of the ratio of amount of executed computations to the cost of initializing actors. When implementing our profiler, we decided to track those metrics in terms of bytecode count, meaning that the profiler tracks the amount of bytecodes that are executed by actors in response to messages that they receive, and also the amount of bytecode that are executed in the dynamic extent of the constructor of each actor. On the other hand, when actors are used as communication endpoints, their main role is to handle the communication usually between different entities of the same application that may be also deployed on different machines. For this reason, we decided to focus on messages sent and messages received by actors. This means that apart from the number of messages, which is a quite basic metric, we also want to track the type or the class of the messages that they receive. And the reason is that by tracking the type of messages, we can also understand what is going on in the underlying application. Often the type of messages we receive gives some hints about why the application is sending or receiving messages and what is the operation schedule on the underlying application. And essentially those two are the set of metrics that we focus on when profiling communication. Before designing our profiler, we looked at other existing profilers for Akka. We, of course, there are other related profilers about Akka, but they don't focus much on utilization and communication. This is a subset of the metrics that they typically focus on. So often the focus is on the mailbox of each actor. Some of them also focus on errors, dispatchers, but we didn't find any profiler focusing in particular on utilization. So for this reason, I think that our profiler can be a complementer to used in addition to other existing tools for it. I would like now to give you a little more technical details about our profiler. I've already said that the profiler is based on bytecode instrumentation. In particular, the profiler is built upon a bytecode instrumentation framework for the JVM, which is called Diesel. Among the nice features of Diesel Diesel can guarantee full bytecode coverage, meaning that it is able to instrument every bytecode that is executed by actors, including those in the Java class library. And it is particularly important because our profiler tracks bytecode count. So if full bytecode coverage is not guaranteed by the underlying framework, we would not have an accurate result in terms of bytecode count when tracking utilization. And I know that, for example, some other tools for Akka, for example, I think Canon, is based on AspectJ, which is still a bytecode instrumentation framework for Java that, for example, cannot guarantee full bytecode coverage. So this is one of the main strengths of Diesel, and our profiler is built on Diesel, which can guarantee this coverage. Regarding some more instrumentation details, the profiler recognizes every actor that is spawned by an Akka application. This means that the profiler recognizes subtypes of Akka detector, and for each actor it instruments some methods. First of all, it must instrument the constructors, because the profiler has to track the cost of initializing actors. It also instruments methods that actors can rely on for sending messages. For Akka, those are the tell and ask method. And finally, the profiler also needs to instrument receive methods. In Akka, every actor is linked with an object, which is a Scala partial function, which defines the behavior that actors should follow in response to a given type of message received. And the profiler maintains a link between actors and those partial function objects, and by instrumenting the latter can track the received messages and also the amount of bytecodes executed in response to messages received. In order to measure the creation overhead and the amount of executed computations, the profiler uses some bytecode counters. Those counters essentially they track the amount of bytecode executed by each thread during their execution. They are kept thread local, meaning that each thread has its own copy of the counter and only it can access to the counter. In this way we avoid locking or synchronization mechanism, and in this way we can also keep the overhead quite low. And intuitively the instrumentation logic reads the value of each bytecode counter at the end and at the beginning of the constructors and receive methods, takes a difference, and in this way it can measure the creation cost for executed computations. Finally, those counters needs to be maintained. In particular, the amount of bytecode executed by each thread needs to be added to the counter at some specific time. And this is done by instrumented basic blocks. The profiler instruments every basic block that is executed by actors. At the end of each basic block, the counter is updated by the size of the basic block. The size is measured in terms of number of bytecode instructions that compose the basic block. And in this way, at the end of each basic block, each counter is guaranteed to be up to date. And I think that here it is particularly clear why we need full bytecode coverage. Because if the profiler cannot instrument every basic block, then some bytecodes would be missed for sure. I don't present any other technical details here, mainly due to lack of time, so I will refer you to the paper in case you have in case you want to read more about that. And I will instead focus on the evaluation. In our paper, we present 3 use cases. In particular, those use cases are related to actor utilization, profiling of load balancing, and communication in computing frameworks. Here in the presentation I focus on the third and the first one. First of all, I would like to start from actor utilization. The goal in this use case is to analyze the effectiveness of parallelism in applications that use only actors to obtain concurrency. In such kind of application, there is no threat. There is no other concurrency mechanisms, like for example futures or runnable. So you have to resort to actor profiling in order to have some information about parallelism. We applied our profiler to a benchmark suite, which is called Savina. It is an actor-based benchmark suite composed of 30 benchmarks written in 10 different actor libraries for the JVM, and of course Akka is one of them. And in particular, benchmarks in this suite use only actors to obtain concurrency. We applied our profiler and measured some metrics mainly related to the utilization of each actor in the benchmarks. And we found both little utilized actors and highly utilized ones. And when utilization is too low or too high, this can pinpoint the presence of some performance problem. First of all, I will start with little utilized actor. If you focus on the percentile on the distribution, you can see that in 9 benchmarks out of 30, at least 20% of actors are little utilized. And in 5 benchmarks, the percentage is at least equal to 50%. And finally, in 3 benchmarks, at least 80% of actors are little utilized. And those 3 benchmarks also spawn a high number of actors, meaning that also in terms of absolute value, the number of little utilized benchmarks actors is quite high. And in some cases, even the number of messages is very high, which means that single messages trigger the execution of only a little amount of computation. Now, when utilization is low, this essentially means that the computations executed by actors are not much more than the bytecodes executed by the JVM for creating them. And for this reason, for some actors, it might be the case to be removed somehow. By removing some actors, which is a possible optimization in this case, we would get rid of actors that anyways would be utilized only little. And this would also have the effect to increase the utilization of actors that survive this optimization. And in this way, actors would be utilized more on average. Another possible optimization is to redesign the assignment of work to actors. Here I'm assuming that the amount of work cannot be changed, because otherwise also the utilization would change. If some benchmark show both little and high utilized actors, then also redesign the assignment of work to actors can be a feasible optimization to solve this problem. On the other hand, when utilization is high, this means that some parallelization opportunities might be missed. High utilization means that sometimes actors could be, let's say, more actors could be spawned, and the work could be assigned also to newly created actors. For example, in Savina, we found that at least in 7 benchmarks, actors are highly utilized on average. However, this optimization also depends on the amount of available resources. For example, I would like to make an example of count. Count has, on average, highly utilized actors, but spawns only 6 actors. If we deploy count on systems where more than 6 cores are available, and if we add more actors, then those actors could be scheduled on cores that anyways otherwise remain idle. In this way, by splitting the work further, assigning work, spreading the work among a large basis of actors could be beneficial for the application. Okay. In the second use case, the focus is on communication. In particular, our goal here is to analyze the communication occurring between workers in distributed computing frameworks. Nowadays, communication is used for many different operations. So, if a user wants to analyze the performance of an application, we think that also analyzing communication can be important. And in particular, this is important in those frameworks that are distributed, because a high number of messages sent can also congest the network in case those quantities are high. In particular, our goal here is to analyze what is going on in two big data computing frameworks that are Spark and Flink. Those are frameworks used for big data applications. More recently, they've also been used for machine learning, computations on graphs, streamings, and so on. And both utilize Akka actors to handle the communication occurring between the master and workers node, while computations are carried on by other entities, and so we don't care about computations here. We set up both frameworks with the same workload, same number of cores, same memory. In general, we try to replicate the operating condition in a way that they are most similar as possible in both frameworks. And we compare the number of messages being exchanged between masters and workers. These are the results. So as you can see, the target workload is a k-mean application. And there are quite huge difference between Spark and Flink, both in the master and in the worker. In the workers, if you consider that Spark sends on average 1.6k messages, then this amount is around 25k in Flink, and in the master the difference is even higher. Spark sends more or less 4k messages and Flink more than 110k. So given that the workload is the same, the operation condition is the same, the difference is quite big. And for this reason, we consider the communication in Flink to be less optimized than in Spark. In the paper, you can also find our analysis on communication. In particular, we correlate the number of messages sent with the data size to trying to understand whether by increasing the data size, also the number of messages sent increases. And we found this to be true in Spark, while the correlation in Flink is a little clear at the moment. We found a behavior which is really not tied to the input set, the size of the input set. And while our results seems to suggest that communication is more optimized than in Spark, we also wanted to validate it to see whether a better communication reflects also in a better application performance. And for this reason, we analyzed the execution time going on in both frameworks. And in fact, we found that the application performance in general, applications running on Spark were always faster than those running in Flink, given, of course, the same workload. So apparently, better communication reflects into a better application performance. Okay, to summarize, here I've presented a new profiler for Akka actors. The profiler is based on bytecode instrumentation. Our profiler targets in particular actor utilization and the communication between actors. And we have used our profiler in different use cases, as you can see in the paper, and we consider it useful for many user needs. Before concluding, I would like to mention some questions that currently remain open. First of all, we use bytecode count for tracking the initialization cost and the amount of computations executed by vectors. But we know that bytecode count has some limitation. First of all, it cannot track any code, in particular if, sorry, it cannot track all code, in particular if the code does not have a bytecode representation. Of course, it cannot be tracked by bytecode. For example, native methods or JVM internal functions are currently missed by our bytecode counters. It also is not representative of the same amount of, it's also not representative of the real amount of computations executed by the machines. So work of different complexity is represented with the same unit. And finally, it is also susceptible to on-the-fly optimization. Our profiler takes measures and makes instrumentation at load time, but at runtime, the just-in-time compiler can remove some bytecode, but still the bytecode has been accounted at load time. this would result in some bytecode not being effectively executed by threads, but still being accounted in the bytecode counters. And this is another problem that we are aware of. For this reason, we are wondering whether we should move to machine instruction count instead of bytecode count. One reason why we choose bytecode count is for its portability, but one open question is whether we should move to machine instruction count and we should prefer accuracy and sacrifice portability in order to have some more representative results. Regarding complementary metrics, apart from machine instruction count, we could also derive from machine instruction count CPU time. This would allow us to answer the question of how often actors are busy in carrying on computation. We already know how much they are utilized, but we don't know currently if they spend all the time busy in carrying on computations or if they stay idle for most of the time. And this is something that we can answer thanks to CPU time. But on the other hand, CPU time is also subjected from perturbations arising from instrumentation code, because executing instrumentation code will alter CPU time that is profiled by the profile. And this is something that, on the other hand, active utilization is not. Finally, we should also expand analysis on the use cases. For example, in Flink, we know that it appears to be less optimized than Spark, but we don't know the reason. So further investigation of the root causes of inefficient communications are currently needed. And that's all. Thank you for your attention, and I'm here for take any questions. Thanks.
What is the overhead of running the bytecode instrumentation?
So currently it is from 5% to 20%, depend on the length of the workload. This is a rough estimation.
So go ahead.
How do you handle runtime errors? So I mean, you were saying you count bytecodes, sorry.
Yeah.
And what happens if in the middle of the block a runtime error occurs? So
okay. The instrumentation at the moment. Okay, you mean, so your question is related to profiling the amount of executed computations. Is that right? Okay, currently runtime errors are not considered. So if there is a runtime error, still this will be accounted.
and do you have any measures on the failure ratio?
Failure ratios of actors? No,
Oh,
no, this we don't have.
Oh, I was just curious about if any of your findings about Flink's performance are news to the Flink community, or they already know that there's something slower than Spark in general?
So the question is whether we confronted this to the Flink community, or if they are.
Well, in part. I mean, you mentioned in future work to find the reasons,
Yeah.
but the Flink people, they already sort of know that they have a problem with Spark, or is this
Okay.
a new finding?
Okay, this I don't know.
Okay.
So because before, let's say, before reporting that, we should really analyze the use case a bit more. What it seems from the results is that Flink is not optimized for small datasets. So this is my understanding so far. So probably by running large datasets, this would change, or the performance between Spark and Flink would be more similar. But for small datasets, I think that you can really see in Flink the problem that I have mentioned before, and this should be analyzed further. Thanks.
I missed your explanation. What's the difference between display fire and common?
Okay, so I mentioned common only because common is based on aspect J, if I'm correct. But actually, I didn't mean to compare my profiler with common. I know that there are some profilers that focus, that for example can already tell you how many messages are sent or received by actors, or how many actors are spawned. I'm not sure if Camo is one of them. It might be. I was just saying that, for example, if you want to extend existing profilers for measuring the amount of bytecodes executed by actors, you need full bytecode coverage. And for example, you cannot do this with Camo because it's based on AFFJ, which does not guarantee full bytecode coverage.
Thank you.
You're right.
Then I have
Yeah.
last question. That you compared your tool with other profilers, and you said that they are mainly based on other metrics. My question is that, do you plan, or is it possible to extend your tool with other metrics, just to use one tool? Because okay, your tool can be a complementer to other tools, but using different tools, it's...
Well, considering the metrics that other profilers are tracking, I don't think this would be a problem. So extending
So you can extend.
extending the profiler is in principle growing. Yes, I don't see any obstacle in that.
Thank you.
Thank you.